So hello, I'm David, second year PhD student at Cambridge, supervised by Sandro Tekela. Thanks for the organizers for inviting me. And today I will be talking about galaxy close pairs at high redshifts using deep WGST data. Um, so one of the main questions is how do galaxies grow their stellar mass? It's either by forming stars from the nearby cold gas or through galaxy mergers. However, comparing to the measuring the star formation history of galaxies, measuring the galaxy merger rate is much more difficult. But galaxy mergers are very important in different physical aspects, such as morphological disturbances and triggering starburst, AGN activity, enhancing star formation rate in galaxies, but also quenching it at later stages. So it's very important to measure the rate of these galaxy mergers. So there are two methods of looking at these these mergers. One is by counting the close pairs, and the other one is looking at disturbed morphologies. So, but from now on, I will be focusing on looking at galaxies which are in close pairs, and in particular, looking at major mergers, which have a stellar mass ratio between 1:1 and 1:4. And looking at previous studies, they mostly looked at the pair fractions up to about redshift 6 and 7. And they found differing trends, so mostly increasing trends, but some studies found flattening or even an overturn. So it's really important to look at these mergers at higher redshifts. So in my project, I tried to push this boundary up to like redshift 9 or 10, using deep James Webb data. And I'm focusing on close pairs of major mergers for a mass complete sample. Uh, uh, JADES was already introduced by Will and Joris previously, so I don't want to spend too much time on this, but I'm using data from the JADES collaboration, which is currently the largest deep survey uh, looking at galaxies, and we just had our latest data release in April. Um, Here, I'm defining three different tiers for my data. So I'm dividing the good south field to two subfields. So based on the exposure time. So there's a deep region and a medium region, and also good north. And we get photometric redshifts from EASY, which is a quick template fitting code, and we are getting posterior probability distributions for the photometric redshifts by a Bayesian approach. And we can also compare these photometric redshifts to all the available spectroscopic redshifts in these fields. So on the lower plot, you can see a comparison between the two. And overall, there is a very good agreement with a small outlier fraction. And we get the stellar masses from an extension of the EASY code called EASY Pi, but also more trustable stellar masses from Prospector, thanks to Charles Simmons. But from now on, I'm only focusing on the analysis using the EASY stellar masses. So in my method, I apply three main selection criteria. So the first is 2D projected separation on the sky. So the close pairs have to be between 3 and 30 kiloparsec separation. Next, for the third spatial coordinate, we constrain them to be at a similar redshift, but we are also incorporating the full photometric redshift distribution by applying the method developed by Lopez San Juan, 2015. And finally, we are looking at major mergers having the mass ratio of 1:4, but in principle, this can be applied to minor mergers too. So now I'm going through the steps of my selection code. Um, so first, we are selecting a primary sample corresponding to the massive galaxies, and we are looking for the space around these galaxies to look for satellites. So as you can see on the plot, which is the stellar mass distribution of our sample with redshift, the red box is the primary sample, so we define constant stellar mass bins. and we look for satellites around these primaries, as the blue box shows. So we are probing deeper. But very important to note that the mass bands for the primary sample are above the mass completeness limit. And we calculate this mass completeness limit by the method developed by Posetti et al. 2010, where basically we find the 5 sigma point source depth of the field converted to the limiting magnitude. And by looking at the faintest galaxies, we eventually get the 90% completeness limit. And overall, for the 3 tiers, this limit is between 7 and 8 log solar masses. So we only look at galaxies which are above this limit. Next, we are creating a mask to look at galaxies which are only within the right angular separation. For this, we use the angular diameter distance, which is redshift dependent. And after that, we convolve the 2 photometric redshift distributions and get something called the redshift probability function. And it's interesting that, so this measures the probability of the 2 galaxies being at the same redshift. So here is an example of a redshift 6 system with very well constrained photometric redshifts. And so, and they have similar masses, so we are quite confident that these are close pairs. And finally, to combine all these selection criteria, we get this pair probability function, which combines the redshift probability, the angular separation, the mass selection. However, we also need to correct for these selection criteria by implementing some weights. So first of all, there is something called this odds quality parameter, which measures the confidence of the photometric redshift distribution. So it's directly related to the how confident are we in the peak of this distribution. And using a cut, looking at a sample of a threshold, we can derive high quality samples. And the odd sampling rate is just the ratio of the galaxies above this threshold and the total number of galaxies. And as you can see on the plot, when we probe deeper at fainter magnitudes, this odd sampling rate steeply declines. And we are using a weight to account for this selection effect. Next, we apply a mass completeness weight because, for example, if we have a primary galaxy very close to the mass completeness limit, we will have a very limited space in mass to look for the satellites around it because they will be below the completeness limit. So based on the galaxy stellar mass function, we predict how many galaxies should be around the primary, and based on this, we derive a weight. And finally, we are adopting an area weight because the survey mosaics have irregular shapes, and some galaxies at the boundaries have some missing area. For example, in this case, it's about 40% of the area is missing. So we also account for this. And eventually, we combine all these weights together and apply it for both primary and secondary galaxies. So I don't really want to show these equations, but I just want to highlight that we are not counting integer numbers of pairs and primaries, but fractional numbers. So the pair fraction in the end will be the sum of these fractional number of potential pairs divided by the sum of fractional number of primary galaxies. These are integrated within the redshift bins of choice. So now this is a compilation of different galaxies we found at different redshifts on RGB cutout. And as you can see, many of them are have very different morphologies. They are very clumpy. And as we saw in some previous talks, it's very hard to decide between a merger or some in situ clumps within the same galaxy. And this code is not accounting for this. but but we can make a selection criteria. We can set a lower angular separation so that we are not dealing with the clumpy galaxies. And so here are some results. So these are the pair fractions versus redshift in different stellar mass bins. And on each plot, the sub-tiers are plotted. So the good south deep, medium, and good north. And overplotted are the averages. And now I just plotted the averages on the same figure, color coded by different stellar masses. And we can definitely say that up to redshift 5, there is an increase in the pair fractions, a slight increase, but in all stellar mass bins. After redshift 5, there might be a flattening or potentially an overturn, but we are still not very confident about the high redshift bins. These might be affected of incompleteness and some other effects. And here is a comparison between some results from the literature. So there's an agreement on the order of magnitude level. However, it's hard to compare them because they apply different selection methods, different stellar mass bins. But yes, there is a good agreement, I would say. And finally, to convert this purely observational measure, the pair fractions, to merger rates, we need to assume a merger timescale. And this is still a work in progress, so this still needs to be done. But there are many different merger timescales based on simulations or observations. But ideally, we would choose something that is redshift dependent and also mass dependent. And finally, just to highlight the future of studying mergers with the ELT, as we heard in the excellent review talk before me, it has an unprecedented resolution and sensitivity. So firstly, we could confirm a lot of merger candidates spectroscopically using the mosaic instrument. And also we could look at some particular interesting mergers using the harmony instrument to study their kinematics and also look at the spatially resolved star formation history, because potentially these mergers increase the star formation rate. So by looking at the scale of this burstiness or quenching afterwards, we can derive much more precise merger timescales. So just to summarize, we successfully applied this probabilistic approach to look at the close pair fractions using the full photometric redshift distributions. And we find a slight increase in the pair fractions up to redshift 5. And after that, a flattening or potentially a turnover, but it's still a work in progress. And finally, by assuming a timescale, we can derive a merger rate. So thank you for listening.
Actually, I have one. What the distance you have between your pair? I mean, and can you observe them with an IFU, like the future ELT IFU of Mosaic, for example?
Yeah, so there are many pairs which are very close to each other.
Okay.
So
you can use the IFU.
Yeah, of course. Yeah.
Good.
So thank you for your nice work. So how strong do you think will be the projection effects? Have you tried to estimate it with analytical methods or looking at simulations to try to measure that? And my other question was, your images showed that a lot of these systems seem to be like compact groups of galaxies at very high redshift, right? So you have multiple pairs inside them, which will eventually merge if these are indeed physically dense systems.
Yeah, so for the first question, we thought about this projection effect, but haven't assessed it yet. So yeah, there could be that. Yeah, so we should use probably a simulation for this to assess it. But yeah, so we might get this projection effect at high redshift, especially. And Yes, so many of the systems are multiple merger systems. So one primary galaxy with 2, 3, or even more satellites. So it's also hard to distinguish because the code would select that even 2 satellites around the main galaxy could be considered an individual pair as well. But yeah, at this point, it's hard to make these decisions. So.
Okay, we have to move on. Let's thank the speaker again. And the next speaker is Luis Baquero. And she's going to talk about tracing stellar mass assembly during cosmic dawn, insight from clustering and stellar mass function in the Cosmos Web Survey. Here we go.